We have limited time, so I say let's do it.
Okay. Well, to start, thank you all for coming this evening on behalf of myself and Beth, my co-chair for COTE, BSA COTE. We are thrilled that you can all make it here, and also on behalf of our committee for the remaining committee for the Committee on the Environment. We are now a full committee group, and we are very excited to be such. So we are working as a collaborative to come up with these talks throughout the next year. So if anyone has ideas, please feel free to reach out to Beth or I or anyone else on the committee. I see Allison here. I'm not sure, Jefferson's on vacation. And I'm not sure if anyone else was able to make it. I'm sorry if I missed your name, but please feel free to reach out to us and check back for our upcoming talks. Our next talk is on September 29th, and that will be a co-sponsored talk as part of a collaborative symposium between CORE, the Committee on Resiliency in the Environment, and ourselves. So we are going to have a week long of talks, and ours will be on the MIT Nano building. So we'll be having a presentation with some of the design team and engineers on that. We are hoping that to also have a tour of the building, because we would really like to start to be back in person, but that is still to be determined based on the events in the fall and how things keep moving. I should note this is all being recorded, so just be aware that it will be recorded for posterity and put up on the BSA's website and on the COTE website. So, but please feel free to ask questions in the chat throughout the talk. We'll try to pick them up at the end or if you're in the middle, if Kevin and Craig are comfortable with that. And also Beth will be putting in the chat the website so that you can get credit for this, because all of us architects know that it's almost the end of our architecture LU year and we need our hours. So please sign up for that if you are looking for credit. So with that being said, I will announce our speakers for this evening. So this evening we have Kevin Bell from Lears Weinstoffel and Craig Garber from Atelier 10. They are going to speak to us about the Dartmouth Anonymous Hall, which is now my favorite name for any campus building, and I'm sure they'll explain to us more about that. But Kevin has been with Lears for, I won't tell the number of years because I think that's telling of your age, and I don't think that's fair. I wouldn't want anyone to do it for me. But you have a degree from your master's in architecture from UVA, which is impressive, but I went to Virginia Tech, so I'm not going to talk with you about that for a little while. But you're also a leader of your firm's technology integration processes, a writer, and works with Northeastern and BAC, all of which are close to all of us, leading workshops and guest lecture or guest. Now I'm losing my words again. So we knew this can happen. Guest crits. So Craig. Alternatively, you went, didn't you? You're at the University of Texas, so I'm less angry about you.
We're not direct rivals, yeah.
Yes. So,
Laura's less angry, but I went to the University of Oklahoma, Craig, so you can't.
Oh, okay, all right. I'm not talking to you, Beth. All right.
This is probably the most sports talk on the BSA ever. Sorry. But Craig is part of the sustainability consultants, architecture, education, and a climate advocate with his firm, as I mentioned, Atelier 10, all very impressive people, and I can't wait to hear more from you. So please take it away, and it should be yours.
All right. Are you seeing full screen? Just want to double check. Great. So as I mentioned, Craig and I are going to talk about Anonymous Hall at Dartmouth College. It's a project that finished up in the middle of COVID. So it's been a little bit of a slow rollout as we continue to learn about the building since it's been opened. We'll talk a little bit about some of the project background, the goals, how we started, and then sustainability vision of the college and for the building. Then Craig's going to talk a good bit about the environmental design, some of the technical analyses that we did for the building early in conceptual design, but also through SD and DD. And then finally talk about some, I won't call them simple strategies, but some strategies for energy reduction that can be really, quite frankly, cost effective or cost effective in the overall scope of the project when compared to other things of equal efficacy, I will say. So Anonymous Hall used to be Dana Hall on Dartmouth College's campus. Dartmouth is in Hanover, New Hampshire. It's for anyone that frequents expressways, it's up 93 onto 89 and just before you hit the Connecticut River. Dartmouth is famous for its green, the green space at the center of campus. And the focus of our initial study was on North Campus where Dana Hall exists, and that's up College Street from the green and from Baker Library that some of you might be familiar with. So as part of the study, we looked at basically the whole of North Campus. Dana Hall itself was a former medical school library. And in fact, that library function had gotten much smaller and moved to another building. And Gilman, just to the south of Dana, was an old lab building that had been replaced by other buildings on campus. And so both had basically been mothballed. So we looked at what made the most sense for North Campus, this former kind of medical campus adjacent to the hospital before it moved off campus, but really kind of cloistered, inward looking set of buildings. And our goal with this project and through the study was to open that up, to really connect it within the campus spaces, back to Baker Hall, back to the green. And what made the most sense coming out of the study when looking at which buildings to preserve, which buildings to demo, was really that Dana was just a better fit for the type of program need that they had moving forward. And so our idea is really to put Dana in the center of an open landscape with paths either side and around, create a new green space in front of Dana that welcomed pedestrian students and people to North Campus, and really celebrate that kind of iconic object in a field and a landscape with a high efficient facade. And really we were looking at a double skin, a double wall facade. And so we had this idea about the building being this glassy envelope around, new glassy envelope around the existing brick building that was the Dana Medical Library. And that's something kind of akin to the Academic Center at the University of Oregon by ZGF Architects. And so you can see Anonymous Hall is at the end of College Street, and the campus really spirals out kind of from the green away to athletics, student life, connection to Main Street to the south. But we wanted to develop and really reinforce some of the interior pedestrian paths that made their way from the green up to North Campus. So we really completed a path that existed in some ways, but never really was completed until this project and the work on Anonymous. So with that, I'm going to turn it over to Craig to talk a bit about the energy goals and technical analyses.
Hi, everybody. So like a lot of universities, Dartmouth has ambitious energy and sustainability goals. They have a campus sustainability office and kind of, climate action plans and things like that. They have energy policies that get down to prescriptive requirements for enclosures and things such as that. These are some of the highlights of their big picture goals. So carbon neutral by the end of the century, moving towards half renewables, within 4 years. We're getting close to 2025, and then 100% renewables by mid-century, and then trying to tackle greenhouse gases as well. Dartmouth tends to be very much focused on energy foremost. I mean, occupant comfort as well, and they care about other stuff too, like healthy buildings, but really energy is foremost, and that was kind of the charge that we got when we started on the project, hearing the folks from the Dartmouth Sustainability and Facilities Office. So just a little bit of background, that Dartmouth had one of the first cogen plants in the whole country, and they're still burning fuel oil. There's no natural gas to this campus. I think it's because of its location. It's in between the Green and White Mountains, so you don't have natural gas infrastructure. So they're still burning oil. They're kind of transitioning the distribution from steam to hot water, and then the plan is to transition the fuel from oil to biomass, because there's a lot of that around in the woods surrounding Dartmouth, and then later to solar and wind to help them meet those renewable thresholds by mid and end of the century. And then next, Kevin. And I'm imagining most of this audience here is in the Boston area, so pretty cold up in New Hampshire, zone 6A, heating dominated, cold winters, a lot of snow, a lot of cloudy days. And so, we always kind of start by looking at the climate and seeing what strategies make the most sense for this particular climate. Okay, next. And when we work with LWA and really with any architect and on all projects, we like to start with the passive design principles first. So I'm sure the COTE population knows about passive design, but we're talking about climate responsive strategies, the stuff that's good, responsible design, the kind of stuff that architects did 100 years ago without thinking, and then we kind of got away from it in the middle of the last century. But for this particular climate, for this project, the principles that we targeted were, because it's an existing building, gut renovation, so trying to keep as much of that embodied carbon on campus as possible. Preventing heat loss, so it's a heating dominated climate, we want to keep that heat in the building, and then balancing that with letting the sun in, using that for passive solar heating. You see that the glacier facade is a southwest facing facade, so trying to balance letting in the appropriate amount of daylight, not letting in too much heat gain, and so on. And then naturally ventilate if possible. In this particular climate, there's a lot of opportunity for that. Next. And then these are some of the specific strategies that we ended up pursuing. So reusing the building structure, we'll get into that in a couple minutes. Compact massing, LWA essentially was following the massing in the existing building, but this kind of massing makes a lot of sense in a cold climate. And we're talking about the surface area to volume ratio. So minimizing, a lot of wings and appendages and more surface area that would translate to more heat loss. Using a responsible window to wall ratio. So you could see there's, you have the southwest facade, and then the other three sides are predominantly punched windows with a rain screen system. So I forget, Kevin, was it about 30% window to wall ratio on the punched windows? It's a very responsible.
Yeah, on the east, north, and west facades were about 30% open there.
And on the southwest facade, and you can see there are little returns on the two ends also. While it has an all glass appearance, there is insulated spandrels, so that's not fully glazed. And having most of our glass facing south, so we can make use of that passive solar heating and bring in useful daylight. The building sort of shades itself, so you could see how it overhangs at the second floor. That provides shading for the ground floor. And then the PV array, which is on the roof, on that superstructure, that provides some shading for the upper floor. Also, the shading is integrated within the glass, and Kevin's going to get into more of that in a couple of minutes. So there are louvers in the cavity within the IGU. And operable windows, you could see the operable units on the curtain wall, and then there's operable sections of the punched windows as well. And then even just in the way the spaces are arranged in the building, LWA tried to keep the offices on the other three facades to avoid, like thermally thermal discomfort in spaces that are occupied throughout the day. Those spaces that are on the south side are predominantly more lounge and gathering and circulation type spaces where people are moving through and transitory kind of spaces. So people can, they have the flexibility to get up and move seats if there happen to be sitting in the direct sun. So that informed the floor plans as well. Okay, next. And we'll be touching on each of these strategies, but we didn't quite get to net zero. We're going to describe kind of the process and the thinking, but these are some of the strategies: the insulation of the opaque walls, the efficient mechanical systems. Once you're getting all your loads down and have a good envelope, then you start looking at the renewable energy. Okay, next. So I just want to talk for a little bit about the kind of our role on the project, what we call environmental design, which is the technical analysis that supports the design team. We like to get started early. In this case, we were brought on, I think, during concept, and our work is more front loaded, and we're trying to inform the design. We work very iteratively and integratively with the architect and the design team. And it's really with the goal of what questions are they trying to get answered? We don't want to do analysis just for the sake of doing it. What are the tricky questions that we can help with some technical analysis to help optimize the design? Okay, next. So I'm going to go through some of those here at a very high level just to show you what kind of questions came up and the types of studies that we did to address those. These are some of the early double skin concepts with different sort of shading options. And Kevin, you can, I think, cycle through these. There's 3 of them. So as Kevin mentioned, that was the beginning point, a double skin facade on the southwest facade. And then I can't remember at what point in the design phase it transitioned to a non-double skin facade. But at one point that was eliminated from the project. Kevin, you could probably give a little more color on that. Maybe you're going to touch on that later.
No, I think the move from a double skin facade to the fused skin, as you might call it, is it wasn't that the double skin facade was crazy expensive relative to everything else in the project. It was just that I think maybe a CM or a contractor would call it the low-hanging fruit. It was the item for which fewer people could or more people could live without it, and we wanted to preserve the energy efficiency of the building. And so quite frankly, we felt we could save money here and work really hard to maintain the performance that the analyses that Craig's going to talk about kind of describe were possible out of the double skin, and maybe even try to improve that when we move to the fused skin.
Right, thanks, Kevin. So a lot of what I'm going to show here studies based on the double skin concept at that time. So the first question that we were trying to tackle, and this is back in concept, was does that DSF really help when it comes to thermal comfort compared to a triple glazed facade? Triple glazing, by the way, is the campus standard for other buildings. Okay, next. So during concept, we're giving more qualitative type of feedback. What you're seeing here are like excerpts from reports where we're showing different types of double skins, some more passive, some more active, and giving like qualitative feedback on considerations, design considerations. Next. And we did do a thermal comfort study, like a multi-tool study where we used Grasshopper and our own spreadsheets and things like that, and evaluating the design at that point against ASHRAE criteria. ASHRAE 55 has set criteria for thermal comfort that has to do with the temperature differential between the surface area, the surface temperature of the glass, and the air temperature in the space, and so on. So what you're seeing here on the bottom is looking at different options, the baseline, which is triple pane versus a couple of different double skins, and making certain assumptions for the glass and calculating the surface temperatures, and then comparing those to the ASHRAE standard to see if it would comply. Okay, next. And what we found that the double skin was actually performing very well as a thermal buffer. So the temperature within that cavity, which I can't remember, I think it was 30 inches maybe, was significantly higher than the outdoor air temperature. And what that translates to is that the inner surface of the glass, like the inside surface of the double skin, was significantly warmer, and that was giving thermal comfort to the occupants. What you're seeing also here, some of you may know that Payette tool, which is a great online tool, and this is a snip from the results. So we looked at case 1 was triple glazing, and case 2 and 3 were 2 types of double skin facades. And it showed here that the triple glazing was not meeting the thermal comfort criteria. It's above that 10% dissatisfied threshold. Okay, next. Then like moving a little further into the project in DD phase, looking again at the double skin, but more about daylight and the visual environment. How much daylight is going to be available? And when we talk about daylight, more is not better. There is such a thing as too much daylight. It causes thermal discomfort and glare. And so we want useful daylight. And we call that visual comfort. So next. So here you're seeing a section through that double skin facade. And in this study, we were looking at different sun shading options within the double skin cavity and giving feedback to LWA and trying to help them optimize it. And so, yeah, and you could see some of the sun shading goals, which are general goals that you would pursue on any project. Avoid overheating and glare, try to maximize your passive solar heating and preserve your views to the outside. Okay, next. So we looked at several different daylight metrics. What you're seeing here is some graphics we call overshadowing diagrams. These are studies at particular points on the facade. You could see a point A and a point B. And that diagram, which if you haven't looked at these before, it's a little difficult to decipher. But essentially, if you can imagine yourself being on that point, being hung from the facade, what times of day do you see the sun? So in other words, and those 2 circular diagrams on the right are showing the sun paths throughout the year, time of day, and the facade orientation, and when that facade would see the sun and when that facade would be in shadow by self-shading of the building. So these are kind of some of the graphic tools that we use to communicate with architects. Next. And then, so we looked at different cases. We always try to set a base case. So the double skin facade had a maintenance catwalk. You could see in that base case, there's like a dashed green line at the floor level. And then we varied that in different ways. We moved that catwalk to the ceiling. We added vertical components at the outer surface, looked at how that would affect the sun cutoff angle, and modeled and simulated the daylight. Next. And these are a couple of different metrics that we look at. On the left is the glare probability. So these are sort of heat maps. If you haven't seen these before, what you're seeing is along the top, I'm talking about these green, I don't have control of the cursor, so I can't point, but these green charts along the top axis is the months from January to December, and along the left, the y-axis is time of day, from morning at the top to midday to afternoon. And wherever you see red, that's where there's a concern for glare. So with this base case, and these are looking at 3 different conditions, different offices, different points. So you're seeing, like in that southwest facing private office in the middle, a lot of red from like 10 to 2 in the afternoon, when basically you got to have the shades down. Otherwise, those people won't be able to work in that office. So that's helped us predict the glare potential. And on the right, sunlight exposure is a metric that tells us what portion of the floor area are going to see direct sunlight. When we talk about daylight, we want diffuse daylight. We don't want direct beams of sun coming in, landing on your work surface or on your screen or in your eyes. So ASE is a measure of the percent of floor area where direct sunlight is a concern. And so what you're seeing here is the base case. And then Kevin, if you cycle through the next few, we did these studies for each of the alternatives too, and you could see how they kind of vary. And this one actually shows with the blinds pulled down, and that's why there's no more direct sunlight. But these are the kind of studies we look at to see, try to assess visual discomfort issues.
I think a lesson here for us, Craig, was not to put offices up against these windows. And so that was a programmatic change and reorganization that kind of came out of this. So it's not always just simply about what the facade needs to do to respond. But sometimes moving a couple offices is actually the better part of valor.
Yeah, absolutely. So we usually have some workstation recommendations. So yeah, next. Those are just some snippets from the different options, but another way of looking at glare are these point in time visualizations. These are false color diagrams. You could see kind of like a fisheye view of the space, and you could tell by the colors in the scale at the right where you're starting to get into like dangerous levels of glare. Not dangerous, like harmful, but levels of concern. Okay, next. Yeah, and then we looked at different times of day, different times of year, and the different design alternates, the base case versus other variations. And in our reports, we always try to pull it together at the end. And this is a summary table of each of the metrics mapped along each of the design alternates and the ones that we're recommending and preferring, and some recommendations and considerations, including the workstations and plan layouts, as Kevin mentioned, and where we felt the louvers would be the most effective. Next. And then we had specific recommendations about the size of the louvers and the spacing and so on. So this is the kind of feedback that we try to make our graphics kind of accessible. We're sort of visual people, and architects often are also. So we find that that's a good way to communicate it. Okay, next we were again looking at the double skin facade and also the punched windows, and trying to assess whether triple glazing would be a benefit over double glazing. And here we started to look at energy performance. We were actually not the energy modelers for the project. The mechanical engineer, Van Zelm, did the energy modeling also. So they were doing some studies side by side. But here we were looking at kind of how the envelope would affect the heating and cooling loads in the building, and how that might affect the mechanical system sizing. So these are just some quick studies of, yeah, that's fine where you are now. Looking at the different cases, triple versus double, how that affects the cooling and heating loads, how that affects the surface temperatures. And when it came to looking at energy issues, obviously that favored triple glazing, because that's going to result in less heat loss. Flip to the next one. And then we zoomed in on some worst case conditions, like the worst peak winter week and the worst case summer. And what you're seeing is like variation in temperatures in the space and on the surface of the glass, and how that informs the thermal comfort. Again, the triple glazing gave a little bit of extra thermal comfort, but the double skin was performing well on thermal comfort because that cavity was acting as a buffer. So what we suggested to LWA is triple glazing is not necessary at the double skin facade, because that's already acceptable thermal comfort there. Next. And then the question that always comes up is, if you go to triple glaze, can you then eliminate the perimeter heating? And working with LWA, we looked at a few different options for the glass coatings, 1 coating versus 2 coatings on triple glazing. And there was an improvement. What you're seeing in that little table in the bottom is the surface temperature at the inside of the glass. And in neither case, even adding that second coating, it does not get that surface temperature up to the point where you can eliminate the perimeter heating. So perimeter heating was still needed even with triple glazing at the punched windows. Next. So the recommendations for this study is at the double skin, the double pane glass is fine. It's more economical. The thermal comfort's acceptable. But at the punched windows, we felt that they should go to the triple glazing, mainly for the thermal comfort benefits. And then the furniture recommendations as well, as Kevin mentioned. Next. Okay, and then just a couple other quick studies. So this one, at this point, LWA had identified glass that had integral louvers, and so we did a little more assessment of verification on that. So Kevin will get into this, but there was an Ocatec glass that had these integral louvers, and so what we looked at, like the worst case day when the facade was receiving the most solar radiation, just to see to what extent those louvers were actually doing the job and what percent reduction you would be getting. And they were actually performing quite well. So that's what some of these, on the bottom are looking at multiple cases, and assumptions for the glazing properties and so on. And then finally, we looked at natural ventilation. We worked not only with the architect, but with the engineer as well. And so they had questions about to what extent natural ventilation was viable in this climate. Next. And so we did some quick studies on trying to determine, just based on the outdoor air temperature and the relative humidity, using weatherfile for this specific location, how many hours of the year could you potentially use natural ventilation? And what you're seeing in that graphic there, all the blue and yellow, the conditions are somewhat favorable for natural ventilation. And so if you mapped out over kind of the operating hours of the building, let's say from 8 a.m. to 8 p.m., you ended up with about 600 hours throughout occupied hours throughout the year when you could go to natural ventilation. It doesn't mean that that we ended up making use of all those hours, because you still have to have a certain minimum airflow to offset your internal loads. And so those considerations I have on the lower left, those are some other drivers that the mechanical engineer was using. Basically during the peak loaded cooling times, we were into mechanical cooling mode. But there are many hours when we can use natural ventilation, and you saw those operable windows on all 4 facades of the building. Nice. Okay, so that's really, that's like quick rundown of some of the studies that we use working with the team to help inform the design. And that at a certain point, again, it moved away from the double skin towards a high performance, I think Kevin called it a fused skin facade, triple glazed. And so we're going to go through 5 strategies now. I'll cover the first one, which is building reuse, structural reuse. Next. So this is the original building, concrete building from the early 60s. A penthouse was added in steel in the early 70s. And Kevin, you have more background than me, so feel free to chime in. Next. And you can see kind of the history of in photographs of the building itself, and some of the beautiful hand-drawn details that are, those skills are now lost.
Yeah, and I think that the note on those details is that I think the R value for these walls is about 2, for anyone keeping score.
Yeah, and look, frankly, energy wasn't a big consideration then. Energy was cheap. And so, before the oil embargo in the 70s, we didn't really think about these things. And then this shows kind of the progression of the existing building, the areas that were removed, and then what was remaining, essentially the slabs, beams, columns, and majority, the foundations, obviously, for the most part, were retained in the new building. And you can see, construction site photo, and some of, part of what was driving the removals was hazardous materials. I think it was asbestos was found in the sealant in the brick assemblies. Was that right, Kevin?
Asbestos in most things, I think was the short answer there.
Yeah, asbestos was a cure-all at this time in our history, and they used to put it in kids' pajamas. We didn't know any better then. So I know LWA wanted to try to retain as much of the building as they could, but it really, because of the hazardous materials, that drove a lot of the decisions. Also, it was a low-performing, as Kevin mentioned, R2, low-performing facade, and this building is really meant to last the next 60 to 80 years, and so the university wanted a higher performing facade, and so we could not achieve that with the previous envelope. Next. And these are some of the takeoffs that LWA did, primarily to support this particular lead credit that we're pursuing for the building life cycle impact reduction, where you get rewarded for retaining and reusing a portion of the structure and enclosure based on the percentage of surface area. So we're over 50%, which should hopefully earn us a couple of lead points, but it's really the embodied carbon benefits that are the most important. Next. And by the way, in that credit, you can exempt anything that had to be removed because of hazardous materials. So, so we're not being penalized for that. Kevin, I don't know much about, do you want to make a point on this?
This is just a fun photo looking up the shear core, and that's really, the main structural element we had to add to basically help this building last the next 60 to 80 years. We treated the building, although it's an existing building, as new, and so the entire lateral system for the building was upgraded, and it's just a fun photo.
Nice. And then finally, we didn't do a detailed embodied carbon study, but we tried to do a high level, quick estimation of what really we're saving in terms of by keeping that existing concrete. And so Kevin pulled out some quantities from the Revit model, over 20,000 cubic feet of concrete structure that's been saved and retained. And that translates into a lot of emissions avoided. So you probably all know that concrete is responsible for a lot of the, some people estimate up to 8% of global emissions, and that's mostly from the Portland cement. So this is really a huge win for the project to be able to retain all this concrete. And on the lower left, we just calculated some equivalencies, like how many miles the equivalent driving miles. And so, yeah, we feel like this is a big part of the sustainability story in the end. I think that's probably it for me. And sorry, I think I probably took a little too much time, but I enjoyed talking about this building.
Thanks, Craig. So the second strategy is highly insulated. And the idea is, target the basics first. So let's get things right on the majority of our facade, optimize glazing, and then use masking and orientation as Craig described. And so that's really what we tried to focus on for at least the three kind of mostly opaque facades of the building. And so our facade it's lightweight. We removed the CMU and brick from the building and didn't want to go back with that same kind of weight. We're trying to deload it a little bit. And so we're trying to optimize the solid, and that's where the college had a requirement for an R30. We pushed that to make that a continuous equivalent. And in order to achieve that, we have 6 inches of rigid insulation outboard of the ABB outboard of the steel stud wall, and then some batt insulation in the steel stud. And that was really driven by a couple of factors. To go much deeper than that, we'd be beyond the limits of the curtain wall snap caps. So we'd be into like a multiple extrusion. We'd also be into, potentially a third layer of mineral wool applied to the wall. So we were trying to be conscientious of maximum thicknesses of materials while remaining economical. So, rather than 5 inches, which would, be a 2 inch and 3 inch thickness piece of mineral wool, 3 and 3 cost the same to install. The system we were using here, which is a thermally improved aluminum system for terracotta, that kind of could be economically developed to about 7 inches, but much beyond that, things got a bit more expensive. And then something we like to do when we have mineral wool on the outside of the building and a rain screen system, which isn't technically sealed, is we use a bulk water barrier. Really, it's a water resistive, air and vapor permeable membrane. But what that does is any water that gets into that cavity behind the terracotta sheets down the face of that membrane. And although mineral wool will dry out and retain its insulative qualities once dry, wet mineral wool is not a very good insulator. So we continued that idea of highly insulated to the roof. We have a minimum of R60 equivalent continuous, and then we get up to about R90 out at the edges just for sloping for drainage. Important when we added this new facade was to push it outboard of the existing concrete slab edges. We wanted to maintain continuity of the insulation basically from the ground up over the parapet, across the roof, and back down the other side of the building. So limiting thermal bridging up at the parapet, and also where we had to project canopies out on the north side where we have an entry. They're improving that connection by using, in our case here, it was a Fabrica tin system, structural thermal break for the canopy steel. And part of that highly insulated, again, is optimizing the open. So we talked about percent glass, proportions, east and west were vertical proportions on the windows. We deeply set them. So we get a little bit of shadowing on the window, just by the natural geometry, or I should say natural, but the geometries of the opening. And then although Craig noted the second low E coating didn't help us necessarily with thermal comfort, at the edge, but it did improve winter U value a good bit. And so we were trying to really make this envelope as effective as possible, and adding an additional low E coating is not a substantial cost premium once you're already into triple glazing. And then obviously important is just the continuity of that thermal barrier. So making sure your glass is in line with your primary thermal insulation. So we're pushed out beyond the studs in line with our continuous insulation on the outside. And then, detailing it so it's well sealed around the edges and tucking that bulk water barrier in. So we get not only a good primary seal between curtain wall and the opaque wall, but we also have, secondary seal, and then we have that bulk water barrier. So a really tight building overall on these sides with the opaque. And so these are some center glass values, but the center glass value on that triple glazing is 1.6, which I think is, pretty standard now, hopefully for folks doing triple glazing, still with good visible light transmittance and some pretty good solar heat gain coefficient. That brings us to the fourth facade, kind of the elephant in the room. Glass on a south-southwest facing facade, all glass. It was really important to us as part of this project that the building feel as open to this new green space to the south, as open to the rest of campus as possible, and inviting to the extent we could. And really being able to look out from inside and connect back to campus was a really critical component of the success of this project. And so in order to do that, once we no longer had the double skin facade, was to find a do everything system. And so that's a system that has improved thermal resistance, R value, lower glare, lower solar heat gain, still provides views, is bird safe, dark skies, and allows us to naturally ventilate in an efficient manner. And something that, it's I suppose a bit of a trick, but as day turns to night, we still get an opportunity to see in through it. So it's a dynamic facade because of the integral mesh, and sort of changes as you move around the building. It changes with the time of the day. So what we were trying to do, because in some respects this was a cost control measure, was to use components that were tested, components that were available, but to put them together in a novel assembly of parts. So we have two types of glass in the project. The first is that triple glazed system, the Okalux Okatech, which includes an aluminum mesh that's highly reflective. It basically forms thousands of little louvers on the facade. And so that uses 4 pieces of glass, and that has a center glass U value of 0.09 itself. And then we paired that, rather than trying to do spandrel glass and provide the thermal resistance with a secondary element on the interior, we incorporated an opaque HPI spandrel panel. And this is also an Okalux product. It's our HPI. It's a vacuum insulated panel that's sandwiched between 2 pieces of glass. And in our case, to maintain the continuity and consistency of that facade as you move around the building, we continued the metal mesh louver layer in that as well. So these 2 pieces of glass work together to really give us an overall system U value of about 0.15, which for a curtain wall is pretty good. We'll still maintaining pretty okay visible light transmittance of 0.31, but reducing this maximum solar heat gain to about 0.22. And again, this idea of tested components. So we want to make sure we're addressing each piece of heat gain. So for radiation, we have that expanded metal mesh and a coating on the glass to reduce convection currents within the units themselves and reduce the amount of transmission through, filling those cavities, the 2 cavities in the triple glazing, with krypton gas. And then For conduction, going to a silicone structurally glazed curtain wall system, basically that pushes all of the glazing outboard of the aluminum framing, which is highly conductive, puts it behind both some backer rods, some sealant, and a little bit of air. And ultimately that reduces conduction at the edge, perimeter edge of each of these panes of glass. The mesh itself, it's pretty simple. It's expanded metal mesh like what Remco House, I think it's Remco House, used on Seattle Public Library, as well as what was used at the Des Moines Art Museum, I believe, in copper. Basically, by the geometry of that mesh, high-level sun is reflected back out of the IGU, and low-level sun is allowed to move through. And much of the light that does make its way through the system is actually diffused up towards the ceiling, and it actually really softens the light overall. What that metal mesh in the system does, paired with the single low-E coating, is for us on the southwest facing facade, is it lowered our heat gain below standard triple glazing by about 60%. But what it also does is delay the peak gain, which is a small thing, but it allows us to, on some days, actually move that peak gain after the highest occupancy. So we're trying to get a little bit of time between when most people are in the building and when most of the sun energy is being transmitted through the building or through the facade system. This is just a quick look at that vacuum insulated panel. It's basically fumed silica core that's encapsulated in a bag, and then there's basically an aluminum element either side that's sealed, and then the space is evacuated of air. And what you get is a near vacuum, and a vacuum is kind of the ideal solution for insulation. And so in a 1-inch panel, you get an R value that is incredibly high for the thickness. And just a quick comparison of how those two panels, the HPI panel on the left of this with a U value of 0.3 and the metal mesh panel with a U value of 0.9 would compare to double glazing here, some more standard triple glazing than even our triple glazing elsewhere on the building. So it's a substantial improvement over, certainly over double glazing, but even over triple glazing. And this is a thermanalysis overlaid with some other thermanalyses for other systems. And you can see what's really important here is that the backside of the HPI panel, which is on the left, temperatures are actually relatively high. And even our triple glazed light has a really warm inside face. So really limits the need for perimeter radiation, but makes it a very comfortable place to be. And you can see the aluminum mullion itself, because it's structurally glazed, is much warmer than what you might expect if you had a capped system with an aluminum pressure plate that was fastened through with all of those tiny thermal bridges. So a critical question is, what does this look like? And what is it like to see through? What the material does, kind of by its geometry, is looking out and up is very difficult. It blocks most of that view up because it's blocking the sun coming in. But looking out and down, much of that view is preserved. And so that looking through. This is a photo from latent construction. But when you're back from it, you really get a good sense of what's happening on the outside. So it is really highly transparent from the inside, maybe a bit like looking through a large insect screen in some respects. And you can see the panels you don't see through are the vacuum insulated panels, the spandrel panels, if you will. As part of this system, it's important to us to integrate the automated ventilation as well as the solar shading. So on the south side, those are automated. A neat trick of this building, and which is made possible by the fact that the glass panels that house the operable lights are opaque. We didn't have to shade of those pieces. So occupants of the meeting spaces that are on either side of the main circulation space, we can natural ventilate regardless of the activity in the space. So if they're giving a presentation to others in the meeting or displaying something on the digital display, they can lower the shades but continue to naturally ventilate. And we thought that was an important kind of element of this system, was being able to allow the building to work as it should at all times. And this just gives you a sense of what those active window openings look like on the facade. They're the darker outlined. And I'm going to run through quickly because I think we are going a bit longer than I hoped. The mechanical systems for this, it's a decoupled system. So we have a DOAS with energy recovery and optimized ventilation. For us, the system of heating and cooling is radiant ceiling panels. And that was really important in a renovation because we had low floor to floors. And so we simply couldn't accommodate ductwork. So the radiant panels pair well with natural ventilation because they're quick responding. So they're able to heat and cool a space quickly, which is important when you have windows that could be opened. And I think it also prevents some of the concerns about condensation that you might get with radiant in the slab. And visually, what you get is a very clean ceiling with very few vents, and you also get a very quiet building. The natural ventilation for the offices, this is manual, so there is a pilot light by the door that illuminates when conditions are appropriate to naturally ventilate, and then it becomes the occupant's responsibility to open their windows. So we have a little diagram and encouragement to get folks to open the window. And then the last strategy, which was economical here because Dartmouth College uses power purchase agreements to put PV on their buildings. So we have a 58 kilowatt photovoltaic system on the roof of the building that helps to reduce our net energy use. Something I think we've learned as a lesson here is that because it was done after our work on the project was complete and was kind of outside of our scope, we really didn't have much control over the final arrangement of PV at the roof. And so they did an okay job, but you can see kind of up in the corner, they could have gotten a few more panels on the roof, and they probably could have optimized the orientation a bit better. We did get PV where we needed it to shade the building, which was helpful. And you can see on the right here, the light coming into the building through that south facade isn't nearly as harsh. It's really a pleasant, diffuse light nearly all times of day and all times of the year. And then again, as sort of day turns to night, it becomes a more transparent facade to look into. Where we've come to, at least with initial kind of early data that the college has shared with us, and since we're in this COVID era, basically our energy is above where we'd like it to be. Right now, our gross EUI is 43, which is well above where we had targeted, and our net is only 38. So we haven't yet gotten a full year's worth of energy data on the PV to see how much energy it's actually producing. But interesting to us is that in COVID, a lot more energy to heat the building, and we attribute that to probably fewer occupants in the building and fewer computers associated with those occupants, and less, fewer lights on. What we're trying to chase through now is that our cooling loads, our cooling energy is higher than we would have anticipated it to. We're up at about 20% of the total. We had anticipated that being, these aren't direct comparisons, but closer to about 7%. So we have some things to look at and fine tune with Benzelm and the college, but we're getting there. And at least it's good to have a good open dialogue with the college and an open sharing of information about the building. That kind of takes us to the end of the presentation. This is just a summary of some of the sustainable aspects of the building, from 5 strategies we talked about to some other strategies out in the site and around the building, some stormwater detention and other elements that we think make it a sustainable building, both inside and out, and for the college overall.
Thank you both. That was very interesting, and we're going to open up to questions now. I haven't seen any questions in the chat, so obviously you've covered as everyone's burning questions to start, but if anyone would like to unmute and ask a question, we would love to use this remaining time to speak with Craig and Kevin further.
Hi, I got a question. It's George here. Absolutely beautiful building, amazingly presented. And we've all been through this in terms of siting, but I just wondered how your decision process went with your kind of glazing emphasis on the southwest facade, which wouldn't seem ideal just in the greater scheme of things, but I assume there are real site reasons why that expression ended up on that side. Is that right?
Yes. So exit out here and go to the diagram. The real generator of this was the ability to look back towards campus. So in our building up on the North Campus, quite frankly, you get good views of the campus itself, a visual connection back. A number of the folks moving into this building, it's sometimes swing space. We'll have some permanent occupants. We're moving from closer to the green, actually adjacent to the green, and so maintaining that connection to the campus. And I don't want to say we're turning our back to the Life Science Center or the medical school, but we really wanted to have an open element. And I know that glass, is highly opaque during the day, but that's why the ground floor has the terrace, has the green space out in front of it, and the glass facade. So it was really generated by that desire to connect back to the campus that's to the south.
Absolutely, that makes a lot of sense. Thank you. Thank you.
Kevin and Craig, we have a question in the chat. It says, very interesting. What is the source of the screen that softens the harsh light? Is this a custom assembly?
Let me get to our bested diagram that it's not a custom assembly. It's actually something that Ocolux had used in Europe previously. It's one of their standard products. It's about 2 inches thick. It's technically triple glazed because there are 2 air cavities. The metal mesh exists in the outboard air cavity, but there is a 4th pane of glass that separates that metal mesh from the interior. It actually allows Ocolux to sandwich that metal mesh and keep it in place between those outer panes. It's aluminum, so there is temperature differentials that occur within that cavity. So the metal mesh isn't actually held rigidly by any element in each of the glass units. It's sort of floated between those 2 pieces of glass. So it's not a custom element. The kind of novel piece of this was that this and the HPI vacuum insulated panel which is the opaque piece, haven't been used anywhere in the US or I think North America prior to this. And I think it may have been the first time that they applied all of these technologies together into one facade.
Yeah, and Francisco, I'll just add, and I could put the link in the chat here, if that worked. Yeah. Okalux is the company, and they make different variations. They make some that have sort of like little mini blinds or louvers within the glass cavity. They have some, I think, Kevin, that are wood, right? Different materials, different configurations. It can be tailored to the specific sun angles. So it is an established company, and they have a diverse product line.
Kevin and Craig, did you have any conversations with the owners about this product being the first in the US? That were there any apprehensions or convincing that need to happen along with that?
We had conversations. I think in those conversations, it was important to note that it was the assembly of all the products together that was novel. It was not the products themselves. They themselves were tested, had been used elsewhere. So that alleviated some concern. I think the bigger concern was on our facade. We had, obviously the curtain wall was coming from the US. This glass was coming from Germany. Our terracotta, I think, ultimately came from Asia. So the actual Dartmouth's biggest concern was getting all of the material to site on time so it could get installed. I think, interestingly, that was the bigger concern, is that we had to ship it from Germany, and what happened if a piece of glass broke. Fortunately, only one piece wasn't broken. It came with the mesh upside down, so they actually had to ship another piece and replace it later.
There any other questions?
Kevin and Craig, thank you so much for your impressive diagrams that have made this easy to understand. Much appreciated.
You're welcome.
There's a question about Conair's toggle curtain wall system. Conair's system was one that we had specified among three. We actually ended up using Wausau's, I think it's Super Wall, their toggle held structurally glazed system. And the reason for that at the end of the day is that Wausau didn't put any they didn't have concern with 2-inch thick glass. That's slightly thicker than a lot of the manufacturers will accept as their standard. Everyone kind of at this point accepts 1 3/4 glass. That's kind of standard triple glaze unit. But Wausau didn't take issue with the slightly thicker glass.
And for everyone here who may not know what a toggle lock curtain wall system is, do we want to define that?
Let's see. This isn't great to show it, but basically a toggle held system, the glass unit itself is married to, in our case, an aluminum channel frame. And that's done with, for us, temporarily holding it in place with some 3M very high bond tape, and then sealing it with a structural silicone to it. So you get an assembly that has a channel around its perimeter. And then basically it has a small toggle that gets inserted vertically and then spun horizontally, some on the vertical members, opposite on horizontal. And by turning it and fastening it, you fasten it back. The actual panel gets fastened way back at the mullion. And what that allows you to do is avoid any metal in between the panes of glass. And what you get is a silicone seal at the face, backer rod, and then a bit of an airspace without any metal or really highly conductive elements out near the face of the facade. And it does have a small, if meaningful, improvement in the overall performance of the facade.
Thank you. That was very helpful. Any other questions? We have a little more time. I don't want to keep anyone needlessly in the evening, but I think it's been a great discussion so far.
I just want to say thank you to Kevin and Craig and you know, the BSA COTE roundtable for having this discussion. I've been really eager to hear this whole presentation, and it was fantastic. I want to say, Kevin and Craig, I think one of the most interesting things to me was the fact that you really leveraged Dartmouth's own goals. You know, you didn't you try to kind of build on those and hold them to the highest possible standard. And I think that's a great lesson for all of us too. Thank you so much.
Thank you.
Yeah, thank you, Ashley. I think that is a really great point about the colleges. You know, they have triple glazing as a standard, but they don't always follow it because often it's one of the first things to get BE'd. I shouldn't say often, but sometimes it is. And, you know, for us, we really, on this project, energy efficiency was a big driver. You know, we had goals from a campus perspective, we had goals from a building perspective, but with each system or consideration, we really kind of back checked it against, you know, whether it was an energy efficiency measure or not. And it's simple to, you know, in some respects to push that through when you can say, well, this actually isn't our idea, it's yours. And surprising, not surprising, I suppose, people really like to hear that they have good ideas. So that might be a little bit of a lesson learned as well. Always give credit to the owner for their brilliant standards that allow you to create an energy efficient building.
I love it.
So definitely more time for questions, but just a reminder that to fill out the form in the chat box, that if you'd like credit for AIA credit for this, Beth, I think just put it in again. And so please, if you're not seeing it, let us know. And any other questions from anyone? I will.
Presenters get credit too?
Yes, you do.
Good. Okay. We need those hours.
I will reiterate that the graphics and the presentation is great, and thank you. We really, you know, from the COTE side, we really do appreciate it. It was I learned a lot, so great for me. Anyone else have a burning question?
There was one in the chat from Lisa.
Thank you. I should have scrolled down. Who else makes the toggle system besides Conair and Wasa?
Trying to remember. Oh, I think they all make some version of it. I think, Laura, to your point at the beginning of this, that sometimes it's hard to remember the words. I'm having trouble remembering the manufacturers at this point, but I think at this point it's a relatively common assembly. I shouldn't say common. It's you can find it from, I think, most of the major providers.
Great. Yeah, Lisa, that means that we'll be coming to you and we're going to spec it. I can see why you're asking. Don't see any others in the chat. Anyone else? Please feel free to come off mute and ask away.
I just want to recognize, I see Josiah turned on his camera too, so I want to recognize him as the design partner, I guess, for the project, and, you know, setting the design direction. And I think you appeared in one of the photos also as made a cameo, right?
Yeah, I was the dean of the Graduate School of Arts and Sciences, and we were in his office.
during the pandemic, you had to stand in as a building occupant. Right?
Yeah, exactly. Right.
Great. Well, thank you all for coming today, and thank you, Kevin and Craig. We really appreciate it. Great presentation. And to remind everyone, next month, the 29th of September, we will be having a presentation on the MIT Nano building, which was a 2021 COTE, National COTE winner. So please join us for that. That information on that will be coming in the BSA calendar soon. And that is part of a week-long symposium that both COTE and CORE are sponsoring. So hopefully you can check out a few of the other talks as well about our overall resiliency. So thank you all, and have a good evening.
Thank you all. And if you think of any other questions, just send them through, I guess, to Lara and Beth, and we'll be happy to answer other questions.
Absolutely.
And thank you again, Lara and Beth, for the invitation.
Thank you. It was fun.
Thank you.